again. So actually, about the homework, I think as the email mentioned, uh, I would want you all to work on piece of paper and separate problems on separate pages and work neatly and all that. Um, but also, most importantly, you should, after you're done, you should scan it in and submit it this Friday by 5 p.m. on Blackboard. Those of you who already took a course with me are familiar with this, but the idea would be that this would allow you to work completely independently of any other sources. So I would like you to work independently on your homework. Even if you get the solution wrong, no trouble. If you made an honest effort, you're going to get full points on that first part of the homework. As I said, that will be due this Friday. On Friday evening, around the same time that the homework is due, 5 p.m., I'll post the solutions to that homework. And based on those solutions, you need to go back and take a look at your homework, correct any mistakes, comment on any things that you might have learned, or if you found the solutions to be incorrect, then absolutely mention that. And then that part two would be due on the following Monday, in general Monday, but if there's a quiz or if there's a holiday or something, then you can always, we can extend that deadline. So that's the deadline on Friday is pretty hard, but on Monday, it's much more flexible. So any questions about the logistics of this homework? Go ahead. Part two of the homework is grading, essentially grading your own homework, part one, with a red pen. So for part one, you cannot use a red pen. For part two, you only can use a red pen. Meaning, if you made any mistakes, you have to correct your own mistakes with a red pen. And even if you made a mistake, as I said, in part one, you'll get full score for part two, as long as it shows that, yes, you made an honest effort, but you made a mistake on part one. So you correct it on part two, and you'll still get a full score. Okay? Questions?
Where can I find the
Scanner?
Yeah.
So I think there are scanners in 1212 lab, is that right?
You can go to the EAPS library.
Oh, to the EAPS
Right
library.
above.
Right, it's on second floor on the other side, I guess the new or the old side of the building. EAPS library, there's a scanner there. And some people in the past have used these cell phone camera type of scanners. If the quality is good, meaning if I can kind of read all your small indices and commas and dots and everything, then it's fine. Otherwise, just to get a good quality scan, you should use a proper scanner. Okay. All right. Any other questions on the homework? I will also mention that there is this discussion forum on Blackboard I had created. So if there's any doubts or questions that come up as you're doing your homework or from the lectures or anything, just post a short note there. You're all welcome to answer each other's questions. Chances are, if you have a question, most likely half the rest of the class has the exact same question. So that will save me time, save you time. Rather than me trying to answer each and everyone's questions independently, we'll post all the questions and answers on the forum. Okay. All right. So very quickly, we were discussing this initial notation last time, which we had developed for working with vectors and working with all these x, y, z components. And I'm not going to call them x, y, z because we want to use indices 1, 2, 3. So the idea really is that there are certain rules with this initial notation. There are these two types of indices. One is a free index, which occurs on both sides of an equation. An example of a free index is this I. So last time I showed you that if you have a vector v, and if you wanted to find components of that vector v in the three coordinate directions E1, E2, E3, you can simply dot v dot ei. I could be 1, 2, or 3. So I is a free index. It occurs exactly once on both sides of the equation. And the other type of index that we saw was a repeated or a dummy index, which occurs usually on only one side of the equation. For example, if I say vector v is defined as v1, e1 plus v2, e2, and so on, this can be written in a shorthand way as summation I1 to 3 of VI EI. Okay, and it occurs exactly twice, usually on one side of an equation, and uh, we also use this summation convention to say that every time we have a repeated index, we are not going to explicitly write that summation. So if you see a repeated index, I, or J, or K in any expression, immediately you have to think that, oh, there's a summation sign implied ahead of that expression. So VI, EI simply means V1, E1 plus V2, E2 plus V3, E3, so on. So these were some of the rules that we set up, and we set up this Kronecker delta property, Kronecker delta symbol that allowed us to use its contraction property to simplify somewhat lengthy expressions. An example of that, let me see if I can disable this. Wireless power off. Okay, so hopefully it won't bother us anymore. So for the Kronecker delta, the contraction property, what it allows us to do is to work with these somewhat lengthy expressions to simplify it. And one of the key examples that we gave for this Kronecker delta was the dot product of two vectors. Okay. Now the idea is that, for example, if you dot product u dot v, we have these components for u, these components for v. We saw that it gave us 9 terms, and we set up this Kronecker delta in such a way that when the two indices that it has, when they don't match, when I is not equal to j, it's 0, and it's 1 only if I equal to j. So the purpose that this serves is as follows. U dot v is equal to all of these 9 terms, which is equal to ui vj delta ij, and of course summation over both I and j. The good thing about this this contraction property is that since the value of delta ij is equal to 1 only if I is equal to j, we can essentially replace one of these indices, either u or j, with the other index from delta ij. So for example, in this case, I replaced j, which means we are contracting over j and replacing that with I. And we saw that it simplified it to ui vi. Okay. So this operation is something that that you need to understand how it works. Essentially, this line right here, this one line right here, is a shorthand way of writing this entire big 9 terms. Okay, so you need to understand how this contraction property works and how these indices work, but it's nothing but pure arithmetic, adding and multiplication. Okay, so it's not any more complicated than that. It's just a shorthand way of writing it. All right, so let me ask you, related to that, a couple of questions. Let's try to evaluate let's see if, okay, if I have some vector u, and if I have my 3 coordinate directions, E1, E2, E3, then I would like you to evaluate u dot EJ, or maybe EK, u dot EK and EK. So first question, is the result going to be a vector or a scalar or what? It's a vector, right? Because the quantity in the parenthesis is a scalar. Scalar multiplied by a unit vector is of course going to be a vector. So try to simplify this expression and tell me what you get. Maybe take 30 seconds or a minute or so. U3. Try again. Let's see. So maybe I'll write that in this way. Um, so this is on the left hand side. I'm asking you what is on the right hand side. Note here that k is repeated, right? So the summation sign is implied, and you cannot have a free index on the right hand side because the free index has to be on both sides. So 3 cannot be on the right hand side. Okay, so take maybe another 30 seconds, see if you can simplify that. And maybe before you try to do that, let's try to physically understand what we are doing here. What would be the quantity in the parenthesis here? U dot ek. What is that? The component of u in the direction of ek, correct? Which, so if k is 1, it's u1. If 2 and 3, it's u2 or u3 and so on. So one way to simplify that would indeed be to try to interpret physically that this is uk, and then what is uk ek? It's u itself, right? If I have uk ek, so I'll write all of that out here. I can write this u vector as ui ei, correct? And then dot with ek, that's the parenthesis, and then I have another ek. So if I were to simplify that, note that this is a scalar multiplying a vector, that becomes a vector, dot with another unit vector. So essentially we are dotting these two, doing a dot product of these two unit vectors, correct? And what that should be, it should just be ui delta ik. Do you agree? ei dot ek is delta ik. Why is that? Why is ei dot ek as delta ik? This is delta ik indeed because the product would only be 1 if I and k are equal. If I and k are not equal, the product should be 0, as dot product of two unit vectors from a basis of 3 would have you. So, and then finally we are left with ek here, and according to the contraction property of this delta ik, I can take this k, contract them with each other. So k and k cancel off, and I can replace that k with I. So I'll replace that with I, and what I would get is ui ei, which is nothing but u itself. It's kind of a roundabout way of describing the vector u itself, but I'll use that property very shortly. So the idea is that if you have an expression something like this, if you have an expression where you have some vector dot product with ek and the whole scalar product again in the direction of ek, what it simply boils down to is that this u is what we get back. All we are saying is that the vector is equal to this vector sum of its components in the right directions. Right? That's what this statement says. All right, so let's see how we are going to use this property. Question, go ahead.
When we say k over here, does that k does not imply ijk, the k belonging to ijk, doesn't
It
imply
is.
something else?
No, k is an index here. So let me maybe write it more precisely.
Is it not a definite direction?
It is not a definite direction. So k can be anything. It can be 1, 2, or 3. So yeah, I think that's a good point that definite directions are E1 or E2 or E3. When I say EI, that I could be anything. I could be E1 or E2 or E3. Similarly, J could be anything, 1, 2, 3. K could be anything. Any of the other indices that we'll use could be any of the indices. So that's right. I, J, K do not necessarily correspond to 1, 2, 3. They can take all possible values 1, 2, 3. Okay. Question?
If I contract with between ui and third ik, and
correct.
We have the k to be the dummy index.
That's right.
It's the same with
Right. So as what's your name?
Kaiji.
Kaiji?
Yeah.
Okay, so as Kaiji pointed out, I chose to contract K here. I could have just as easily chosen to contract I, right? And let's see if we get a different answer then. So I can write this as del UI delta IK, that's the parenthesis, and I have EK outside, and I'm missing, and it didn't, anybody notice that? I'm missing an underline there. So that's minus 0.5. Um, um, so that's the same expression, but instead of contracting over k, I'll contract over I this time. I'll cancel off these i's, I'll take this k, replace that here, and what I get is uk, sorry, not delta, but ek. uk ek, is that equal to ui ei? Yes, because k and k are dummy indices, which just simply means that summation going from k going from 1 to 3 of uk ek, which is equal to the summation going. So all that this is saying is that summation going from k 1 to 3 of uk ek, which is also equal to summation going from I equal to 1 to 3 of ui ei, and they're all exactly the same u. Okay. All right, so we'll get more comfortable with this initial notation as we go along. Let me point out where we were going to use this. So last time I had showed you this permutation symbol that we were going to use uh, for, for describing a cross product of two vectors. So if you remember, we said cross product of two vectors u cross v would be this perpendicular vector to their plane, u cross v. And if we were trying to express that in terms of components, how would that shake out? So I have u, that's here, that's the vector v. And again, note that I'm not going to repeat I here. If I were to repeat, say for example, a sum of I going from 1 to 3 here, and again a sum going from I to 3 here, when I use the summation convention, it becomes ambiguous. Okay, so no index must occur more than twice in any expression. Okay, so if we expand this out, we again get those 9 terms, and um, as opposed to the dot product, in the case of a cross product, we have E11, E1 cross E10, E2 cross E20, and E3 cross E30. The rest are the non-zero terms. So to handle all of those non-zero terms, we came up with these with this alternating or permutation symbol epsilon ijk. I pointed out that this represents 27 different values, right? I could be going from 1 to 3, j 1 to 3, k 1 to 3. Of course, that's 3 to the power 3, 27. And you could list all of those out just as I did list out the first one up here. Not necessarily the first one. The first one would be epsilon 1, 1, 1, which would be 0, right? In this case, I'm just giving an example of a non-zero value, which is epsilon 1, 2, 3. It's in a cyclic order, so it's 1. Anti-cyclic gives me -1. So using this symbol, we are going to try to express what a cross product of two vectors is. So in order to do that, I'm going to make use of, let me actually delete this part. I think it's in your handouts, but I'll come back to that. So let me consider this expression, epsilon I j k ek. There are how many free indices here in this expression on the left hand side? Free indices. How many free indices on the left hand side? 2 free indices. Those are I and j. They are repeated exactly once. They occur exactly once. They are not repeated. They occur exactly once. So I and j both are free indices. And the dummy index or the repeated index is k. So what that means essentially is that this, since k is repeated, it immediately implies this summation. What we are talking about is summation of I, j, k ek. And let me ask you this. How many possible values do we have here? On the left-hand side, how many possible values are we talking about? How, and so let me step back here. How many possible values were here? 27. Because there were 3 free indices, right? Here I have only 2 free indices, I and j. So you give me a value of I, give me a value of j, and that's a particular equation or a particular expression. So E, or I could have epsilon 1, 1. So yeah, if k is 1, but since k is repeated, it would have to be epsilon 1, 1, 1 E1 plus epsilon 1, 1, 2 E2 plus epsilon 1, 1, 3 E3. That would be one equation. So a total of 9 possible values on the left-hand side. And of course, on the right-hand side also, we'll have 9 possible values. But what does that mean? Exactly the way that I've written it here. Since there is a summation on k, if I expand that summation, I get epsilon ij1 e1 plus epsilon ij2 e2 and so on. So you give me a value of I, give me a value of j, and now the left-hand side and the right-hand side become a particular equation, right? It's not coming, it's all right. So let me write that out here. Epsilon I j k e k. That, since k is repeated, is simply means summation of k going from 1 to 3, and the exact same expression, epsilon I j k e k, which as I just said is epsilon I j 1 e1 plus epsilon I j2 e2 plus epsilon I j3 e3. So if you give me values of, let's say, I equal to 2, j equals to 3, then that implies that I have a particular equation now, epsilon 2, 3, 1. Right? Epsilon 2, 3, let me write it here, yeah. Epsilon 2, 3, 1 E1 plus epsilon 2, 3, 1, 2, 3, 2 E2 plus epsilon 2, 3, 3 E3. Let me ask you this. Any of these terms 0? Second term is 0. Why is that? Second term is 2, 3, 2. So second and third term both are 0 because here 2 is repeated, here 3 is repeated, right? So any 2 indices of the epsilon, if they are same, the result is 0, 0. So what I get here is epsilon 2, 3, 1 E1. In the same way, you could write out a different value for epsilon I equal to 1, j equal to 1. You could have something. And in the same way, you would have 9 possible equations. Do you agree? That I have these 9 possible values of the left-hand side, right? So that's what we're talking about. Excuse me. All right. So for these 9 possible values of the left-hand side, I've expanded out. Excuse me. I've expanded out the right-hand side, and now I'm going to write that right-hand side in a slightly different way. I'm going to write that as using this definition that we came up with. epsilon ij1 is equal to ei cross ej dot with e1, okay? And that E1 stays here. Similarly, this guy is epsilon ei cross ej dot e2, ei cross ej dot e3, and their unit vectors are multiplied outside. Can you tell me what this expression is? That's right. So it is expansion of ei cross ej. You see that? We just did this exercise of a vector can be expressed u dot ek is simply u. So what that means is if I take a vector dotted with ek, that gives me its component k, uk, and uk ek gives me back that same vector. That's exactly what's going on here. I have some vector, its component in the E1 direction. So component in E1, and this is component of that same vector in E2. That is component of the same thing in E3. And if I take those components and multiply them with their basis vectors, I should get back the same vector, which simply is equal to ei cross ej. So that's what's hopefully written on your handouts. Right? Maybe I'll write that more explicitly. Dot ek and ek, which is equal to ei cross ej. So essentially, all of this exercise simply to prove that epsilon ijk, that was the left-hand side, epsilon ijk ek is equal to ei cross ej. And now, using that, we can substitute this value back in the expression for the cross product. So the expression for the cross product of those two vectors we came up with was ui vj ei cross ej, right? This ei cross ej, we are going to replace it with the expression from the next page. So we are going to replace that with this. So what we get is epsilon ijk ui vj ek. So, question? Go ahead.
This coordinate system drawn about this thing.
This.
The system drawn in the box.
Okay, this one?
Yeah.
Mm-hmm.
Is it according to the right hand?
Yes, E3 is coming out of the plane. No, so E1, E2, right hand rule, 3 should be pointing out of the plane, right? Yeah, that's okay, no worries. But here we have, so the whole point is if I give you two vectors, u cross v, the cross product of two vectors is expressed in terms of its components using this. On the right hand side, how many repeated indices do we have? I, j, k, 3 repeated indices, which means on the right hand side I have a triple sum. A triple sum, which, so the way that we would read this expression, as sum of I going from 1 to 3, sum of j going from 1 to 3, sum of k going from 1 to 3 of epsilon ijk, ui, vj, and ek. So this is a long expression. How many terms in total? A sum of not 21, 27, right? Because 3 times 3 times 3. So for each value of I, when I goes from 1 to 3, I get 3 values of j, 1, 2, 3, 3 values of k, 1, 2, 3. No, so that will be taken care of by the properties of epsilon jk, epsilon ijk. There are 21 zero terms in epsilon ijk. So the non-zero terms will only be 6. Only 6 non-zero terms will be remaining, correct? And those non-zero terms are actually listed out somewhere. Let's see. I think, yeah, that comes a little bit later. But essentially, this is a triple sum. So normally, I would not write all of this summation of I, j, k, and all that. The moment you see this boxed expression, which has I repeated, j repeated, and k repeated, as soon as you see that there is a repeated index, you need to put a summation sign, not explicitly, but you need to understand that there is a summation sign over there. So this sum of 27 terms will give you u cross v, the cross product of two vectors, which I'm sure most of you are used to calculating cross product using that determinant and crossing all of that. So this expression captures all of that process, okay, because of the properties of this alternating symbol, epsilon ijk. Okay. And you'll see that we'll use these symbols, both the Kronecker delta and the alternating symbol, quite often to simplify these complicated expressions. Right now, it might seem like this is more complication than the way of writing it in terms of matrices and all that. But very soon you will see that there are expressions which have 5, 10 repeated indices. 3 to the power 5 is how much? Well, 3 to the power 4 is 81. Another 3 is 243, is it? So 243 terms, you don't want to be writing all of those terms out by hand, right? You cannot do that by vector matrix multiplication, whichever way you want to do it. So for those complicated expressions, this type of indicial notation is very convenient. Because the good thing is that on the right hand side of any indicial notation, any expression in indicial notation, things are simple. Ui is a scalar, it's a component. Vj is a scalar. Ek is a direction vector, is a unit vector. So even though if we were to expand it, we would get 27 terms in this case, or many more terms in some other case, the underlying expression captures all of those complications. Okay. So anyway, we'll keep working on this, and it'll take some time for you to get used to this, and therefore you'll also get homework exercises based on this. But if any of these rules or expressions that I'm working with are not clear, go ahead and ask your questions. All right, so a couple more properties of the cross product. As you already know, cross product is not commutative. U cross V is not equal to V cross U. It's of course equal to minus V cross U. And it is, what is this property? That's not associative. What property is that? Distributive. So cross product distributes over vector addition. It's distributive. Associative means that you can add three vectors in any order, right? A plus B plus C is equal to A plus B plus C, and, or A plus B and C. Okay, so related to the cross product, we have this thing called the scalar triple product of three vectors, which of course I'm sure you're all familiar with. But let's see how we'll express that in this indicial notation. The physical meaning, of course, as you well know, is that if I have three non-coplanar vectors, three distinct non-coplanar vectors, then I could draw a parallelepiped out of these three vectors, and the volume of that parallelepiped would be given by the scalar triple product U cross V dot W. And another good thing of a property of this scalar triple product is that you can do a cyclic rotation of the vectors around these two operations, cross and dot, and you would get the result as being the same. Physically, what does that mean? It means that no matter which order you compute the volume in, as long as you are doing a cyclic order permutation, then the volume does not change. But the sign of the resulting scalar, which would be corresponding to sort of a negative volume, if you were to think of the order of uh, as as a non-right hand rule order as being a negative sign, then that is being captured by these other two expressions written down here. So, all right, let's see how you would do that in terms of the initial notation. So I have U cross V dot with W. U cross V, as we have just proved up there, is epsilon ijk ui vj ek. So that's my U cross V right here. I'm going to take a dot product of that with WLEL. Here's another question. How many terms in this equation, this expression on the right hand side? Let's first talk about free indices. Any free indices? Free indices. No free indices. Because free index better be on the left hand side also. No free index on the left hand side. There are 4 repeated indices on the right hand side, I, J, K, L, which means how many terms? 81 total terms. I do not want to be writing all of those out, right? So we have a sum which is a 4. There are 4 summation signs here. We already interpreted that. And the way that we are going to work with this is just as we would work with a scalar expression. All we are going to do is scalar arithmetic. So I will write that as epsilon ijk ui vj, and since I have one vector dot with another vector, all I need to do is to ek dot el. What is ek dot el? Delta KL, right? Which means that if K and L are not the same vector, their dot product would be 0. If K and L are the same vector, meaning either E1 or E2 or E3, their product would be 1. So indeed, the expression Ek dot El is delta KL. We'll write that out. I'll write WL also here, and then I'll write delta KL. Can I do that? Can I change this order? Can I take WL here and write delta KL this way? And why if I can't do that? Because these are all scalars, right? So I can simply take them out of the vector multiplication and multiply them all together. Now I can contract this L and this L from delta L, delta KL, and I'm going to replace that with K. So what we get is epsilon ijk ui vj wk. Okay, and to draw a nice box around that. And how many terms in this expression, in this boxed expression? There are still 27 terms, which is a big reduction from 81 terms initially. So there is indeed a triple sum here because I, J, and K are repeated. And we already know that 21 of those terms are going to be 0 because of the properties of this epsilon I, J, K, which is exactly the same 21 terms that were 0 for the cross product. And therefore, if you remember the expression for the scalar triple product, we get the same non-zero 6 terms that we had for a cross product. So I won't go into the expansion, but if you want, you can expand all of the 27 terms and see that only these 6 non-zero terms will be remaining. Okay? Questions? All right, keep digesting. We'll see how that goes. So we're going to switch gears here, and I'm going to introduce a new physical quantity. Well, it's not really a new physical quantity. You have been working with tensors ever since your sophomore year, but you may not have been calling them tensors. So what is a tensor? Um, Tensor is a physical quantity, just like scalar and vectors were physical quantities. Tensor is a physical quantity that acts upon a vector to give you another vector. Okay, so it's a sort of a more general, uh, more generalization of the concept from scalar to a vector. Scalar only had a magnitude, vector had magnitude and direction. Now tensor is a higher order quantity which acts upon a vector to give you another vector. And I already mentioned maybe sometime back that stress is a tensor. And we'll talk about what is the vector that it acts upon. Anybody know what vector does stress act on and what vector do you get out of it? So we'll come to that. Stress acts on a normal vector. Similarly, strain is a tensor. Strain also acts on a normal vector and so on. Here's an example. So the way that we are going to express these tensors are with capital letters. And we are going to say that T acts on U to give me V. That's the way that we are going to express the tensor operation. Anything that acts on a tensor to acts on a vector to give me another vector is a tensor. Question?
And the tensor here is two-order tensor.
It is. We'll talk about that. So in particular, this is a second order tensor because it takes a vector to give you another vector. There are higher order tensors also, which we will come across later on. But here are some examples: stress and strain, an identity tensor. Anybody, any guesses what an identity tensor might do? Right. So an identity tensor is, for example, if you give me a vector, I give you back the same vector, then I have an identity tensor, right? Here's a projection tensor. For example, let's say, maybe I'll actually explain that with here. So a projection tensor, I'll come to that. A good way of visualizing what a tensor is. In the book, I mean, there's some good discussion about what a tensor is, but you can, it's difficult to kind of visualize what a tensor is, something that acts on a vector to give me another vector. It could be lots of things, right? But here's one way. So the idea is that a good way to think about tensors is in terms of its action on an arbitrary set of vectors. What is an arbitrary set of vectors? Think of this ball of arbitrary unit vectors. Okay, so let's say each one of those red arrows is assume that this is any one of those red arrows. So if you think of all the possible unit vectors at a point, you would kind of surround that in a sphere of these pointy vectors, infinitely many arbitrary vectors at a point, arbitrary unit vectors at a point. Okay. So the idea would be that a tensor would act on any one of those vectors to give you another vector. For example, if I pick one of these vectors, let's say this one, the tensor T acts on this vector to give me another vector, which could be something like this guy. So this tensor acts on this vector to give me this vector V. The same tensor T acts on this another vector to give me this vector, yet another vector to give me this vector. So in effect, this tensor maps this entire sphere of arbitrary possible vectors out to a whole ellipsoid. This would actually turn out to be an ellipsoid, you will see later on. This will be an ellipsoid of those mapped vectors. So on the left hand side, I have arbitrary unit vectors U, could be pointing in any direction. You pick any one of those vectors, the tensor acts on this and takes it to a new vector V. The tensor operation can change the direction of that vector It can change the magnitude of that direction. It can completely annihilate that vector. It can do lots of things. But the result would be an ellipsoidal shape, going from a sphere of arbitrary vectors to an ellipsoid of mapped vectors. Okay. Um, Last couple of things, and then we're done. So the same process, this process of a tensor acting on a vector to give you another vector, can be done in terms of components. In terms of components, if I have a vector u, it has 3 components. I will act, the tensor will act on these vectors and give me a new vector v with 3 other components. So the most natural way to represent a tensor in components is a matrix. Because this matrix T acting upon a vector u just by matrix multiplication, 3 cross 3 acting on 3 cross 1 will give me a 3 cross 1, right? So this is the most natural way of representing tensors in components. And just like you had scalars which had just one component, one magnitude, vectors which have 3 components, tensors have these 9 components. These 9 components which indeed depend upon a specific coordinate system. Just like a vector can be expressed in one coordinate system or another coordinate system. The coordinates that you have in these 2 coordinate systems will be different. The components that you have in these 2 coordinate systems will be different, but it's still the same underlying physical quantity, a vector which has magnitude and direction. It does not depend upon coordinate system, right? Exact same way, a tensor is a physical quantity. Stress at a point is a physical quantity. Strain at a point is a physical quantity. It does not depend upon your coordinate system. So if you pick a different coordinate system, the one here, you might get 9 different components which refer to the same exact physical quantity. Stress and strain are both physical quantities. They do not depend upon a coordinate system, but if you change the coordinate system, the components change, still referring to the same process. So how do you visualize a tensor? You visualize the tensor in this manner with these 2, one a red sphere of arbitrary unit vectors and the other a blue ellipsoid of mapped vectors. These 2 balls essentially put together is a tensor T. Okay, it's a second order tensor T. All right. So I think I'll let you digest all of that today, and we'll come back and meet on Wednesday. All right? Question?
The scalars have magnitude and the vectors have magnitude
Not just 2 vectors, but one set of vectors to another set of vectors. The tensors have tensor is a map between one set of vectors and another set of vectors. It's not a particular. It's not like we have. So yeah, opera means that it can stretch it, it can rotate it, it can change its units. So operation is just a sort of a generic term like an addition operation or a multiplication operation. If I take a scalar multiplies a vector, how the operation is extended. That may not be the only operation. It's a generic term for a tensor operating on a vector to give you another. There are special cases where a scalar you can say a scalar alpha, for example, multiplied by an identity tensor That's a tensor. Like, it's clear by itself.
Is it bounded by some gradient?
So let me. Yeah. So okay. Yeah. We talk about all that in the next time. Question?
For this presentation, do we
You just have to work neatly, and your writing and your scan and all of that should be legible, should be understandable by me.
okay,
Yeah, it's
okay.
just
Okay.
neatness.